Hello, good afternoon, happy Sunday. Hope you're having a good day. It's very bright and warm, well, comparatively warm here. We've had some really long weeks of sub-freezing temperatures, and now we're well above freezing, so feeling pretty good here. Even maybe an hour ago, I wasn't sure what I was going to do today. And there's some things I wanted to do, but I don't feel like I have concrete enough of a plan for those things. And I want to try out some things that I haven't really used significantly before. So we're going to go on a little bit of a journey. But the way into this for me is going to a space that I have tried before. So like not a specific project, but like a domain really. And what I hope to get out of this is, well, first of all, have an entertaining series. And then also stretch myself a little bit. So hopefully this will work out. The downside of this, potentially, is that I will be working out of a physical book, which I cannot show on screen. That said, this book, I believe, is available for free online. As part of a university course that is shared among a lot of universities. So I'm hoping that if you are watching this stream, this series, that you're able to find those resources. I'll do what I can to show them to you, to share them. And then, but we're gonna go off, because I don't like to do anything by the book directly. We're going to go a little bit off the reservation and try something new. So here's what I'm thinking. And I'm looking at the book right now. It's in my hand. So let me show it to you all. I got this book as a gift this holiday season. And I've wanted this book for a while. Essentials of Compilation, Incremental Approach, and Racket. So this book, at the time that the course materials inside this book were being created, the approach that they were espousing was novel. And the approach was, rather than build a monolithic, complicated compiler, because if you've not tried to build a compiler or even do any phases of a compiler before in a class or on your own, they are immensely complicated because there are so many things to be concerned about in order to produce, a usable language and one which compiles to efficient code. I say code, it doesn't necessarily have to be, assembly code or machine code. There are lots of different targets for compilers. But the essence of this book is, so rather than building a monolithic compiler, you build lots of tiny little phases. And each phase produces a new intermediate language, is probably the best word for it. But they have different properties of each intermediate language. So there will be a phase which is remove or like do constant folding, essentially do partial evaluation. There is a phase which is turn complex expressions into atomic expressions. And so forth. So that's what I want to try today. We'll get started on one, and the twist to it is that we're not going to use Racket. Haha, big surprise. So I've been wanting to do a project with another language for a while. I've mentioned it multiple times on stream. You can probably guess it if you're watching right now, and that is Gleam. And Gleam is a neat little language, and I'm going to go ahead and switch. So I don't know if you've seen their webpage with the cute little starfish, but it is a language that compiles to the Erlang runtime. It also compiles to JavaScript, and it is a very type-safe language. So this is potentially the challenge here. Racket typing is optional, in the sense that it is like a Lisp on steroids, right? It has basically everything you could want out of a Lisp. But in the end, its types are lists and atomic constants and so forth. So there will be some challenges. Racket has struct definitions. They're not the same way. They really just define they're kind of like records are in Erlang. They are and I'm sure I'm going to get excoriated for that comment, but they're basically like a named list. You have this struct is named this, and it has this many fields. So you're providing structure, and it's not just an open list, but it's still really untyped. Now Gleam will force us to have types, which will produce kind of a challenge. But hopefully what we'll get is that we will be able to create the intermediate languages fully typed, and the transformations between them. So if you're wondering about this, what the resources are, so this is the GitHub page of the compiler course. There's lots of information here that you can look into. The contents of the book are in this repository. And we're going to be going off of, where necessary, the student support code in Racket. They also do this course in Python. I don't know why. Python's popular, I guess. But because Racket is more similar to Gleam than Python is, we'll probably use the Racket examples and translate where we need to. Okay, so I don't know how this is going to go, but we're going to get started. So I've got Gleam installed, and I'm sorry if you can't read that. Let me bump up the size. So the Gleam command is all you need. And I didn't mention, this is going to be another challenge that we run into in this project potentially, depending on how long we run it. This book does compilation to x86, specifically 64-bit x86 assembly language. So I'm not sure whether we'll tackle that today, but at some point we're going to need to be able to run the examples in a virtual machine of some sort. We might start like a Docker container and use macOS Rosetta to run that, because I don't yet want to focus on the details of learning ARM assembly language in order to be able to do this project. So I think that we'll produce the x86 code. We just might not be able to run it for the first session or two. Maybe we'll figure that out next week. Okay, so Let's get started. I'm going to make a new project. Let's see what we do with Gleam new. Okay, so those are all options. So we're going to do an Erlang project. It doesn't really make sense to compile this to JavaScript and then, have to go from JavaScript to x86. So we're just going to skip that part. Okay. So we're going to do Gleam new, and let's call this Essentials of Compilation. This is, very verbose. Yeah, that's fine. Okay. Okay, so what do we have in here? And let's just go ahead and open this in the editor. Oops. So we get source and test. We get a Gleam toml. Looks very similar to a cargo toml. So it's going to pull in the Gleam standard lib and the unit testing framework. Cool. And we get a README. We'll want. God, doesn't it look like Rust? It is a little bit. So this, yes, I want to install the Gleam extension. I'm surprised I don't have it installed already. There we go. Okay. Zed has been, I don't know if you all use Zed at all, but it has been updating like every freaking day lately. Really frustrating. Okay, let's restart again. Okay, so now we're fully up to date. Okay, so this is our our file. I don't know that there's anything in here that says about what the name of this file needs to be. I understand that it turns into, like, the name of the file turns into the module that is generated. So let's see if we can do what can we do with Gleam? Gleam build, and let's see what happens. So it creates a build directory, and so dev Erlang essential for the compilation ebin. Okay, so it makes some files. Hi Chris, welcome to the new project. Okay, so it makes a file this, and it makes a main. Okay, and it's not entirely clear to me what this is going to do, but let's go ahead and rename this file and see what happens. Okay. Let's call it compiler.gleam. That's probably not a good idea, but since this is going to be a standalone project, we're not distributing it as a library. Let's see what happens when we do Gleam build. Okay. Okay, so it makes a compiler beam, and then I guess this is like, let's clear that out first before we, and let's see what's created when we rebuild, because maybe it didn't clean something up. Okay, so this is probably a specific thing where it's making an entry point for the application to start up. Okay, and this, if you've not seen this is a .app file for Erlang. It tells how to start a package, what its dependencies are, and so forth. These are the modules that are created or generated. It's not saying that it starts anything specifically. So there's probably something here that, let's do Gleam run. Okay, so now it's complaining it doesn't exist. So there's probably something about it needs that file to be named something specific. What other fields are available here? Let's have a quick look. Let's look at the docs. All right, Gleam toml config file reference. So that's fine. So we could do application start module. Let's see. Command line reference. What does Gleam run do? Okay, so you can give it the module. All right, well, let's just rename this compiler and see what happens. Because I think it's based on the Gleam. Yeah. Compile. Or build. Okay. And then if we do, let's look at the build directory again. Yeah, so now it's named something different. What if we do Gleam run? Okay, so that does what we expect. Okay, close that. So we just needed to name it something different if we wanted to name the file. So let's rename this compiler test.gleam. Okay, we're going into the book. Compiler. Okay, so let's look at. We don't need to. Let's see. We're gonna jump to if you're following along with the book. We're gonna jump to chapter 2, I believe. We don't need the preliminaries. There is a bit about partial evaluation in the first chapter that we may make use of for constant folding. But we're going to jump right into chapter 2, which is integers and variables, and it starts with the L-var language. So let's get there in my physical book. Yes. Hi, Evan. Good to see you. Yes, we're going to do the Siek book. It is something I've been wanting to do for a while. And there was a point at which I attempted, and this may be a fun follow-up project or, redirection later. I attempted to build or use this strategy. It was more based off of Joe Politz's course that is taught in OCaml. When he was at Swarthmore, I believe, and but I was trying to compile to Beam bytecode. So the virtual machine for Erlang has a bytecode target. That didn't go so well for a number of reasons. We were doing. I was trying to do it in Elixir, and there were certain bits of help from types that I wasn't getting. So I'm hoping to alleviate that with Gleam. So we'll see how it goes. Okay, so in the first chapter they introduce a language called L-int, which is just there's no variables, and we may actually go ahead and implement that. Implement the interpreter for it as well. Yeah, I think we need to. I'm going to roll back to chapter 1. We need to get L-int done, and then we can go to L-var. So we don't need to know about grammars, pattern matching. I am not going to cover basics of compilers. I'm sorry, that's not what this stream is about. But we're going to do a lot of the stuff that they do in this. Okay. So let's just make a new file, and this is going to be, let's call it L-int, and we needed to define some structs here. And I'm just going to put these in comments. what is it slash in Gleam? I forget. Or is it pound? No, it's not pound. It doesn't like that. Okay. So they do stuff like in Racket, it's like struct int value to describe an integer constant or literal, I guess you could say. And then they also define struct prim, which is a primary operation or primary expression, which is an op and a list of args. So, you know, you could think of this as ... but it's probably structured. So we'll want to think about how to do that. So an example they give of how you might put these together is they define -8 is prim with the symbol minus, right? And list of 8, and they had defined above, define 8 as int 8, right? So this is the sort of structure that they're going with on this. We need to kind of emulate some of that. And then they go forward to define some primitive operators, which are like read, which reads an integer from standard input, and they define the implementation of that in a C file. So it would be like linked with after the fact. And then there's like add left and right. And no, I'm sorry. They're saying this is what you could do, but they're actually saying you should do this sort of thing instead. So they're not doing that. So instead of that, it would be more like prim read and empty list, no arguments. Okay, so then we need to apply these rules to categorize the ASTs as predicate. Okay, so there's some bits about inductiveness over expressions. So if an expression contains another expression and it follows the rules, it is itself an expression. And then finally there's a program node. So a program node is like this, and I don't know what this thing is for, this empty list, and there's some expression in it. It's info. So we could be like, this is a struct program, and it has info and body, where body is an expression. Okay, and they're talking about pattern matching, which we don't need to worry about because that is built in the language. Okay, so here's our first thing. So we need to define some types. So let's go to the Gleam language overview, and wow, that is small. We're bumping it up for the stream. So data types. So you can have tuples, which is just a literal and the basic product type. So you can have custom types. So this is like an enumeration in a sense, but you could think of this more like these are constructors for that type. You can define records where the constructor contains fields in it. So we'll probably do something like this, where in the L-int language we need to have an expression type. So type, let's call it expr, And this could be an int with we need to be very clear about this. It needs to be more restricted than just number int. So we should import Gleam int and use the int type. Okay, let's say int is int. Okay. And then we have a primary, which remember they were defining as. Let's use the same ones. They have value here. That's probably best to reuse that. This doesn't actually create, you know, like a named field when it's compiled. This name gets removed, so it's very much more similar to Erlang records, and I think some of them are implemented as Erlang records. So we have a primary expression, or primitive operator, and this is going to take an op, which we're going to define that op here in a moment. We'll call it prim op, and then it's going to take. This is where we're going to struggle a little bit. But I think it's going to take a list of expressions. And this is args is that how you define that? So lists. Lists. Okay, so we'll do list like so. Okay, so we need to define prim op, and this will just add variants to as we get them. So they have read and neg, so negate, and plus, and I think that's it. There's also minus, which is different from neg, but we might, and I'm going to call this negate, just to make that clear. And here's where we may have a conflict, in that this is very like untyped way of doing things, but what we might want is to just have prim op in there, and read takes no arguments, negate takes an expression. So these are mutually. Hello, Medela. Welcome to the stream. So negate would take one expression, plus would take two, minus would take two. That might be a different way to do it. Let's go ahead and do that. I kind of like that. The challenge is that we may get too far off the beaten path, so to speak. But let's see how that goes. The other thing here that is a little bit weird about the formulation that they have is that you can rephrase minus by factoring in a negate into the right-hand operand and turn it into a plus. So I don't know if we will need to do that. Or if this is going to get in our way for now. Okay, so now, so let's make a type which is program, and this is program, and it takes honestly, we're not going to have the info yet. I'm not sure what they're using that for. So let's just give it a body, which is an expression. And that's essentially what we need for the the partial evaluation bit that they have in this chapter. So they define an interpreter, and we can probably go ahead and make that too, just for now. And we will probably use for the interpreter, we'll use the built-in Gleam IO stuff to read an integer. So Gleam IO, and we need int as well because we're doing that. So let's go ahead and make interp expression. I'm going to make it out a full word, even though they call it that. So E is an expression. And this is going to, and I forget how to write, yeah, I know. How do we annotate the type there? Okay, so it's just like Rust. The syntax is very similar. Okay, so this is going to return, this is going to return an int. That's the goal here. So let's do match. I'm learning Gleam as we go, folks. Okay, case expressions. It is case. Okay. So we're going to do case E, and we match on it. So let's add the missing patterns. Yay. That's nice. So if we have an int value, we just want to return value. Okay. So if we have a primary, and this is, we probably want to fill out gleaning some Gleam. Thank you, Chris. So if we have a primary expression, what we want to do is interpret the operator inside it, the operation. So let's make a new function, which is interpret op, and we'll do that. Interpret. And this probably doesn't need to be fun. It doesn't need to be public. So if we get op as a prim op, and this will return an int, and we're doing mutually recursive functions here. So let's add the missing patterns. So if we have minus, this is going to be, there's A and B here. What we want to do is do interpret expression of A and subtract interpret expression of B, right? We're just building an interpreter as the first pass. So if that's the value here, we do interpret expression V, and then we negate that. What's wrong here? Did interpret? Oops. Interpret. There we go. Okay, and that live coding. You'd think I'd be used to it by now. Okay, so A and B, and we need to do interpret expression of A plus interpret expression of B. So this is the sort of thing you always do in interpreters, right? And then the read, we need to read a, we need to figure out how to read an integer off of IO. Okay, so let's look up the hex docs. Gleam IO. Nope. Okay, go back to hex. Gleam. Is that part of the standard lib? I'm betting it's part of the standard lib. Okay, yeah, there it is. So let's look at Gleam IO and what functions are in there. There's also possible it's something in int functions parse. Okay, so we could read a string and then parse it, and I don't know, rather than using the result just like panic, the equivalent of panic. Gleam does have this use expression, which is kind of like do expression in Haskell. It's pretty nice for signal or for syntax trigger. There's this result try, right? If you do it with use, you just get the thing. The problem is here. We can put panic. Okay. Should almost never be used. Yeah, well, we're building a dumb interpreter, so it's probably fine to panic. So let's look at this result.try. So we need to import Gleam result regardless. Is there no IO read? Let's have a look. Gleam standard library. The question is, there's also this dynamic decode thing, which is pretty interesting. The very dynamic decode. Very first sort of system like this that I've seen. It's really interesting. It feels a little bit like Serde in Rust, except that I don't know. It's super unique. I can't even describe what it's like. So I mean, we could do something like this. The main problem is, do we need to import an Erlang module or make an FFI to get to like read something off of standard in? Because there's the functions are debug, print error, print line. There's no like read. I guess that makes sense, given that like this standard lib is supposed to be for both JavaScript and Erlang, and you don't have standard input in JavaScript, right? At least not necessarily. You might have it with Node.js. So maybe there's some package that we need. So let's look on HexPM and just look for Gleam packages. Gleam Erlang, which I think we already import. So let's see. Gleam Erlang. We can do get line. Okay, I think this is what we want. So we don't actually need that. Gleam Erlang. Is that right? Yep. Okay. So now we can do Erlang. Do we not have that in here? Ah. Okay, now we've got it. So LSP, help me out here. Erlang dot getLine. Okay, so this returns a result, and we can give it a prompt, which we'll just do that. So it returns a result or a string. So we need a result dot try, which takes a result. Again, we're just building the interpreter here. This is not like super important code, but we kind of need some of it. Okay, so the next thing we need is a function which takes a string. Let's get an example here. Okay, so function, right, so it takes a string. Let's look at the result package. So I think that we probably want okay, so try no flatten. I mean, map is fine. Maybe we do case of that. Right, so let's explode that. Error, we're going to do the error panic. And there was an example over here of how to panic. Panic. There's also let assert. Yeah. The problem here is we're going to need to okay, let me take a step back because we want to do that. But we're going to wrap it in a, we need a result.try because we want to also, or it's actually, it was then? Alias for try. Okay, so this function will also return a result, and then we'll do a case on that and panic if it's error. I wish there were a direct like unwrap type thing on result, like there is in Rust, but oh well. Okay, so if we get a line, then we want to do int.parse on that line. So the result module try. Right. Oh, there is unwrap. Okay. So we will do result.unwrap. Oh, no, it returns a default error. I kind of want to panic. Looked like there was also lazy unwrap. Let's try that. Okay, and then this is a function that will just panic. Could not read panic as. Is that how it goes? Could not read an int. Okay. So int parse, and this is about the types lining up, the Erlang getLine error. So we might need to, because int parse returns nil. If it doesn't succeed. So we need to make that, those types line up. Honestly, this is starting to feel like let's pull this out into its own function. And this will return return an int. Honestly, that's what we should do. Okay, so we could potentially use the use syntax, like I mentioned before, is kind of like, you know, it does the monadic comprehension, right? So we could do let line the problem with this is we're still going to have to handle the fact that the Erlang, let's rename this readint. Can we rename symbol, please? No. Okay, let's say readint. That Erlang getLine returns something with a very specific error type. So we may have to map error on it. So we'll do use line result.try. For a regular function call in an anonymous function. So the example you're doing here, right? So this is just like, this is the monad, basically, and everything that follows this gets put inside the function that's the trailing argument. So you could think of it like a bit like pipes, where, but not exactly like pipes. It does have piping as well. So yeah, looks around for a burrito truck. Don't make me, oh, make me want burritos. Okay. so now it's like the main problem with this is that I need to use map error as well. So we could maybe do result.map error. And we will ignore the input and just return nil. And then it has the same type as we can do int.parse here. Of line. Excuse me. I'm going to say let red is that, and then we'll do, I don't know if this is any better than doing it inline then. We could also pipe this. We could do, piping might be good. So Erlang get line, and then we pipe that to the placeholder goes there, and then we pipe that to result.try. Placeholder goes there, and then we get the line, and that does int parse. How am I not? Oh, I need parens there. Okay, so now we'll do case result. It's complaining about it not being used. So if the error, we do panic, and we don't care what this is actually. Could not read an int from standard in. Okay, and then if it's okay, then we return I. Not the prettiest, but actually this is the piping felt good. I think there's a way to make this sort of thing shorter. I think we can do this. Yeah. So there was a way, and I don't remember if it's here. There was a way to see the intermediate stuff where it would compile to early. Yeah, so here's what our thing looked like before, and here's our main. Okay, so this is like a wrapper that it generates. That makes sense. Okay, so what I want to see is what happens when we compile this to Erlang code. Hi, Isaac. Yeah, we're doing Gleam. All right, so we're going to build, and let's look at the Erlang code that's generated. And this is not unsurprising, a lot of it. So there's, get line. It does map error, so it's, turning that into nil. And there's try, and there's, so it names that. Yeah, okay. That does exactly what I would expect. That's great. So if there's an error, then we're using Erlang's, error with the panic, so forth. And then if it's okay, it returns I. So I think it's really neat to see the Erlang code, because the Erlang code is completely desugared, right? You're getting the Erlang as it's going to be executed, basically. Now you're not getting the bytecode is down here in the beam file that's generated in the ebin, but what we are getting here is, where does this stuff come from? You can see that our types here are getting expanded into just tuples, which is pretty cool. So the thing I took away from the first time I looked at Gleam was it produces really efficient Erlang code, honestly, which is cool. So that feels pretty good. So we have our little interpreter. Now the next section, no, we could try some things on this, I guess. Let's see about do we need to import this? We probably do. L-int. Yeah, never used. Okay, so we're gonna do is there an IO printf sort of thing? IO, we could do debug, yeah. So let's make a little program. And I kind of want to import all rather than doing this sort of thing. The other thing that we didn't do is potentially we didn't do an interpret program, right? So let's make that. And I think that we can make this interpret expression not public. This takes a program and returns an int or panics. And so do we just do p dot, yeah, p dot body. So let's do interpret expression over p dot body. That's what we should do. Okay, so now we've got let's make a program, and that program is going to have a body which is an expression, and remember an expression is an int or a primitive op. So we're can make a prim in this sense that like it actually makes this. You can't really have this type just directly inhabit a variant without the contained thing. It's not the greatest. So let's do plus, and that takes takes 2 arguments. Let's give it an int, and let's do 8, and let's do read. Is that right? What's wrong here? Oh, so we need l-int.prim. So I think this is going to get a little bit messy like that, but we got this. Let's do io.debug. Do we need let? P. Am I missing a paren here? Let's wrap it in that. I'm not getting some syntax thing here. Let's look there. Yeah, I mean, we don't need semicolons. Let's break it down a little bit. I would love to. And then we don't need to qualify them. It's a little bit better. What's wrong there? Okay, it's really just that I'm missing a paren. Okay, we can get rid of that bracket now. Okay, what's this value is being called as a function? Okay, we don't need to call it. We just need to say do that. Okay, so then we're gonna do IO debug of interpret p. Okay, so let's. I have pretty good confidence that this will work because we've got the LSP going. But let's so we built it. Let's do Gleam run, and let's give it 7. Okay, so it could not read an int from standard in. What's wrong? And there's the stack trace. So get line. The other possibility is that we need something from string to strip. So let's look at the string library. String trim end. Or we can just trim both ends. Yeah. So let's import Gleam string. And then we'll do string trim. Okay, we're going to have to turn this into an actual function. Line. We'll do line string trim int parse. Do it like that. Will that work? Okay. You can tell I like Elixir. Okay, so let's build that and we'll run and add 7. We get 15. Okay, so it was just a little bit of our, our implementation of read that was broken. Okay, so the next step that they give in chapter 1 is a partial evaluator, which is mostly about constant folding. So the example they give, and we'll just kind of write it in the comments down here, because we're going to make partial evaluation below this, is they say if you have, and this is all Racket, remember, if you have plus read minus plus 5 3, you don't want to, because these expressions never change, 5 and 3 are always going to be 5 and 3. Next time you run it, they're still 5 and they're still 3. And the results of these of plus, like adding 5 and 3 together, doesn't change either. And inductively negating that doesn't change either. So as long as you have constant expressions at leaves, you can, in the compiler, evaluate those expressions such that they're no longer they no longer need to be emitted directly. And this is often called constant folding. They're calling it partial evaluation, which makes sense. So what they're saying here in the book is what you would want to translate that to is read -8, and that's the Racket pseudocode. That's not actually what the AST would look like. So what we want to do is implement that evaluation. So in their figure, if you're following along in the the stuff in the website, in here in this repo, what they do next is give code for a simple partial evaluator for this. So we're going to translate that code right away. So let's go ahead and make those functions. So there's partial neg, and this is, let's not do bottom up like they do. Let's do partial evaluate for expression. E is an expression, right? And this is supposed to return an expression. Okay. So case E, let's add the missing patterns. So if there's an int, we return int I. Like there's nothing to do there, right? If there's a prim op, and I would love to be able to explode this these patterns here. So I don't know if just to like do them in line, right? So if it's read, then we leave it as prim read, right? If it's prim, and can we add missing patterns? There we go. Nice. Okay, if it's prim minus, let's move this one up a line. So if it's negate, then we can call partial neg on okay, so this is expression 1. They say partial negate of partial expression E1. Right, so you have to, this is about can you reduce this expression to an integer? If you can, then you can apply the negation to it. Okay, and we'll define that function now. So this is the function they started with. So this takes an expression, and it returns an expression. So this one is much easier. If it's an int and there's value in it, then we do int minus v, right? If it's a primitive operation, then what we return is a prim of negate p. Except negate takes an expression. Oh, we just rewrap it. Right? So we're saying this is like it's being unwrapped here and then partially evaluated. And then if it doesn't come out to a constant, then we need to rewrap it. So that's what this negate thing here is. Now we could do, I could just say the only other option is that it's a prim and I don't need to rewrap it. And we do that. That's probably best. Okay. So we need to implement partial minus and partial plus. So let's do partial, we'll call it partial add, partial expression E1. This is, oh, whoops. I wish it hadn't reordered those, but I think it's probably was trying to do them in it's trying to do them in alphabetical order, which is fine. E2. Okay, so we need to put E1 in here and E2 in here. So again, we're going to do something similar to this. Partial add. E1 is an expression, E2 is an expression. And we're going to return an expression. Okay, so partial add is if we do case of E1, E2, so we're making an anonymous tuple there. And if this is int A, int B, then we return int A plus B. Anything else, we return, we have to do the rewrap, right? So we do prim plus of E1, E2. Okay, and then we have one more, partial subtract E1, and it's going to look basically the same as partial add. So at this point, what I'll want to do when we finish this is I'll want to write a test. I think this is a good time to figure out how to use Gleam unit. And let's just copy this, except we'll change this to minus. And this will be A minus B. What did I do wrong while you're not formatting? Weird. Oh, is it the comma? Do I not need the comma? Help me, buddies. Format. Okay, so right. Okay, the issue is way up here. So this is, we need E1, E2, partial sub, partial XB. Okay. Now what's wrong? Oh, so I need to actually put the bang there. And then this needs to be like so. Okay. Because tuples, there, you can't just put random parentheses around it. Oh, thank you. Very nice. So let's not construct the tuple. Thank you, Gleam, for making something so lovely. Okay, so now, oh, we don't care. That's a, both of those is a don't care. Okay, very cool. I like that. I like that very much. I'm curious how that compiles. I'm guessing it compiles into construct a tuple. Let's have a look. We can jump down to partial add. Yeah, it basically makes a tuple. Well, you just don't have to construct it yourself. That's nice. You know, on the one hand, I could do a lot of this in Elixir as well, but there's just sort of a feeling for me about Gleam, which is that this is pub. It feels like Erlang with types. with strong types. I don't know if that's a weird thing to say, but okay, so this is for partially evaluating a program. We're going to write a test for this. Let's do that. I want to get to know the tests. So here's an example. Okay, so they have, yeah, they end in test. All right, so let's let's make a new, let's copy this, make a new file, L-int test.gleam. Okay. It needs to be pub fun. Okay, so we'll call this partial eval test. Okay, so we're gonna make a program, and I need to import L-int. Can I just import everything? Help me, Gleam documentation. Unqualified imports. Yeah, there's that. No, we don't need to do externals yet. Because like if this are we need negate plus minus read partial. Okay, so we're gonna basically do the example that I was oh, they have one here. So I'm looking at an example. Oh, we need program as well. Program. So we're going to make a program, and we're going to have plus, which is going to have int 10, and this is an example in the book for an exercise, I believe. And that's going to contain prim minus, I'm sorry, this needs to be wrapped in prim. Okay, minus, which is going to contain, I'm sorry, that's not minus, that's negate. And that's going to take plus prim plus 5 and 3. Okay, so plus, I might rename these to add. That would be nice. Add and subtract. Okay, so plus 10 is the first argument. The second argument is negate of plus 5 and 3. Okay, so we've got a program, and what we want is P partial should dot equal program. So we can go ahead and do that. This is 5 plus 3 is 8. Negate it. That's -8. Add that to 10, and we should get int 2, right? What did I do wrong? Found name, expected one of this. We're missing a paren somewhere. Okay, so this needs to be int, right? The 5 and 3 are not direct expressions. Okay. Can we do Gleam test? Okay, so that's not used. Minus is not used. Okay. So it did pass. So let's make a new one. Let's make something that has read, which cannot be reduced. So we'll use that example they had on the previous page as a very straightforward one. They did plus read minus plus 5.3. That was their Racket example. Okay, so we have a program. It's going to have a primitive op, which is plus, and that's going to take a primitive op, which is read, and another one which is negate, and that's going to take another primitive op which contains plus, and that's going to take int 5 and int 3. Okay, so let's do p2 partial should dot equal. So we have a program, and this is what it should evaluate to is plus read -8, right? Okay, so we'll do program. This can be primitive op because we still have the plus. And it's going to be another primitive op here, which is read, and it's going to be int -8. All right, let's test that again. Zoom, it works. Okay, so chapter 1. Now there's some bits here where what I might want to do to clean some of this up. Let's see how far the language server will help us. So if I want to rename this symbol, that didn't do anything. Fun. Okay. What's the GitHub workflow? Just runs the test. Nice. Let me look at the README before we make a commit. Okay. I'm not going to push this to... I haven't made a GitHub repo, so we'll do that in a moment. This stuff isn't that helpful because we're not publishing the hex. An implementation of the book Essentials of Compilation in Gleam. And let's put some links on this. github.com. And that was, let's just copy that link and Gleam.run. Okay. So I'm going to add README. And this is chapter 1, the L-int language. The problem with that, without the underscores, it looks like lint. And we'll say this is interpretation and partial evaluation. That's what we got done. Cool. The only other thing I might do is make a test for interpretation. We kind of have that in here. That's okay, I guess, for now. And we have about half an hour left. Let's get into chapter 2. And if you all have any questions about what's going on, what we're doing here, then we will. I'm happy to answer questions in the YouTube chat, or just drop them in the comments later if you're watching this after the fact. Happy to answer them. Okay, so the next thing I'm going to do, because I always do this stuff open source, is we'll go to my profile and we're going to create a repo, new repository, and it'll be me, essentials of compilation, and public, and we don't need to do any of that. I guess we could choose a license. I can do that later. Okay. Remote add, origin, that, and let's push main. Okay. And we do have GitHub workflows set. The test thing, branch, master, main, and pull request. Okay, so now it's running. Let's go look. It should be really snappy because we have almost no code here. Cool. Okay. Nice. So let's go on to chapter 2. So this, what they do, we're gonna go ahead and make a new thing here. This expands on, oops, rename please, Gleam. This expands on the L-int language to create the L-var language, which is basically the L-int language but with variables. So it says the concrete syntax of the L-var language is defined by the grammar presented in figure 2.1. So expression can right, so the concrete syntax is a variable or let expression. And okay, so they're basically adding the variance. And what we might need to do here is because they're freely extending this, we could potentially get problems of conflicts. This is not a encapsulation kind of extension. It's actually add new variants to the types, essentially. So we can't, I mean, we could wrap, but then we're going to have, the L-int language contained inside the L-var language, and we're probably going to miss out on some efficiencies there. So what I'm going to do is I'm going to copy these types into this, and we might need the partial evaluation. We're not going to do interpretation yet. I don't think that this chapter does. Oh, okay. So they are doing... they are doing that. Okay. So I think we might need to import with type aliases. Okay, so to prepare for discussing the interpreter for L-var, we explain why we implemented an object-oriented style. Oh, geez. It says, throughout this book, we define many interpreters, one for each language that we study because each language builds on the prior one. There's a lot of commonality between these interpreters. We want to write down the common parts just once instead of many times. A naive interpreter for L-var would handle the cases for variables in let, but dispatch to interpreter for L-int for the rest of the cases. Okay. Problem with this naive approach is not handle situations in which an L-var feature, such as a variable, is nested inside an L-int feature. Okay, so to make our interpreters extensible, we need something called open recursion, in which the tying of the recursive knot is delayed until the functions are composed. What do they mean by that? Like lazy? Following code uses method overriding. Okay, so they're using classes in Racket. Okay. I don't know that we're going to have that same opportunity. Let's look real quick at the features that Gleam provides for us that we might be able to take advantage of. I think what's going to get in our way, and this is actually why the Joe Politz's course, I'm sorry if I mispronounce his last name, but Politz, his is in OCaml, and he takes a slightly different approach. I think this approach can still work for us, but honestly, I don't know if any of you have looked at the Crafting Interpreters book. I got about 5 chapters in, and I was writing the thing in Rust, and then there were just too many Java-isms. It was like either things that are completely unnecessary or paradigms that don't translate at all. So yeah, it is interesting. Like, I think you learn a lot from the Crafting Interpreters book, and his approach is like build an interpreter and then go back and like look at it and see, oh, here's how you can turn that thing into a compiler. You were using some of the same infrastructure. So it's an interesting approach. This is much more like build tiny little languages and evaluators and translators. That's what compilation is. It's translation from one language to another. That gradually get you what you want. So what they are, I think what they're suggesting here is that you can define we could potentially do this with higher order functions. What is generic functions? Okay, so that's where the type is unbound. It's like a type variable. That's interesting. So in the Racket code, they're defining classes where each of those classes defines this interpret expression. And it looks like there's an argument which is sort of like self or this on that type. So with, Lisp is not pure, right? So you can get situations where you can pass an argument in, and objects or object oriented in this case is the idea, and it would so for the L-var language you kind of need to set something in the environment of the current expression when you assign a variable as part of evaluating the expression. So but what we need is a bit to work in Gleam. We would need something a bit more be referentially transparent, right? So we would want to return something that has the result of the expression and the modified environment. So we'll need to think about that. The question is, do we need to build an interpreter, or can we get past that and instead go to generating the next language? I'm not sure yet. Okay, so let's go ahead and do this basically by copy paste. I don't think that's going to be sustainable, but we need it for this pass. So let's go ahead and get all this in there. Actually, just copy the whole thing, and then we will update this. So in addition to a primitive op, we have var, which is going to be a string, and we have let, which is going to be interesting. I actually think that we need a var type. Okay. There's a problem. This is a term and this is an expression. Term. The thing I wanted to solve was that this is going to take a var, which is going to be a var term, because you can't have an expression on the left hand side of a let. and this is going to be binding, which is going to be an expression, and then whatever follows is what gets evaluated, and we'll just call it expr. Not the greatest, but this is sort of the abstract syntax of that. It's usually shown as let var expression like so. That's what that translates to, or that's what it would look like in Racket. Okay, so that's what we're building, and now we've got problems of we need to rework all of this, right? So we need something to put results in, bindings, right? Okay, so this is like we need to give the interpret exp a new argument. And I think we need to know a little bit more about some of the types available here in Gleam. So records, sure, we already did that. Generic custom types. There's the dict module. This is what we want. So we'll need to have that. So let's import that. And we'll make a dictionary. And these are implemented as maps in the Erlang VM, implemented as objects or the map type in JavaScript. So we can insert. And I think that what we want is you know, I think I want to get rid of this. We'll have extra wrapping. Well, let's just use string because the other possibility is that there's symbols that we could use. I don't know if there are symbol types in Gleam. Constants? No. Strings. Yeah, there's no symbol or atom type unless we're using the Erlang thing. Okay. So what we need to do is make a new dictionary. We probably need to specify the type on that. Let's look like this. Okay, so the key type, yeah. So let's make a type. Dict of string to integer. Okay, and that probably doesn't need to be pub, but we can do new. So now we have an env here. And what we need to return is an int and an env. So if we just have an int, it just returns that, right? If we need to handle all the other cases too. But if we have a primitive op, we need to pass in the env, and all of the types of these things need to change because now we've got state, right? In addition to the computations. So if we have var, so the interesting thing here is get returns. Here's another thing where we will need to panic when we're interpreting. So var is, and let's rename. What we need to do here is let's say get var. We'll have that be something that does similar to our read function. This is kind of a built-in, but it'll need to panic when the variable is not found. So let's do env name. We'll make that function later. And that doesn't mutate the environment, so we can just return the env as it was originally sent to us. And then now let takes a variable and a binding and evaluates an expression. So we need to interpret the expression, we're going to do we need to interpret the expression given in binding with the existing env, and this is going to be new env. Okay, and then we need to dict insert, and what does that take? What's wrong here? Okay, well, let's match on that. Yeah, sure. Okay. So dict insert takes the dictionary and then the key. So the key is var, and put the result in there. And then what we do is interpret expression. And then we are going to do expr and bound. Okay, so basically this is how let bindings work, right? You evaluate an expression, you bind it to a variable, and then the contained expression can look in its environment for that variable if it's referenced. Okay. 319. Okay, let's keep going. We're close. So we need to start passing env here. Oops. And this is, all of these things are going to return this, right? So this is just passing everything through, right? And this is going to return env. So an op does not, what's wrong here? Oh, there we go. Okay, so we're going to have to do some unwrapping here. the the interesting thing is, though, we can if you think about what this what the semantics are here. We want to evaluate these. The thing is that this doesn't have to return an updated environment, because it is not possible for a primitive operation to create a new binding that escapes and goes up. So we can actually just do this. Right, because we don't care about any changes. They do not escape the scope of that expression. But because this is, go down into the expressions and evaluate those, you have to pass it in, and you have to return what the result of it is. Or do you? Maybe you don't have to. Is this the secret? Maybe we don't have to. You know what? We don't. This, with the way that the AST is structured, things are lexically scoped. So if we make a binding, that only lives for the length of this let expression, right? So we don't have to ever return the env. It never lives beyond the extent of the current expression. So, and let's rename that to new env. So we really only care about evaluating that expression, inserting it for the scope of this call, right? So now we can go back and leave this. Like there's no way we just need to propagate things through. We don't need to return anything out of these. Okay, so let's implement get-var. It's going to look real similar to readint. And this is going to return, has to return an int. So we need to do let result, or we could just do case dict get env, and that's going to take name. Okay, if it's error, what we want to do is panic as we'll say referenced unknown variable. and let's just add name to it. Can you not do that? Okay, we'll just leave it. And then if it's okay and I, then we just return I. Okay, that was actually a lot simpler than readInt. readInt has to deal with IO. So okay, so now we need to think about doing partial evaluation. I don't, but let's hold off on that. I want to see what they do next in the book, and maybe we can put a pin in it for today. Okay, so what we should probably do is make, as our last bit today, make a test for L-var. And we'll copy a lot of this in there. Okay. And we need to import L-var, and we need var. And I'm going to comment out all the partial evaluation for now. Okay, and then it just doesn't care about an interpret. Okay, so let's make interpret test. Let's make a program, and this is going to take an expression, so I want to make sure that we get some let bindings and some variables in it. And one that does not have read. Okay, so let's do let. Let's import that. So we have let, let's say x. I'm using an example from their book. This is an expression int 32. Okay. I'm sorry, they use x1. Let me put it down here where I can actually see it and not have to turn my head so much. Maybe that'll work. Okay, so x1 is 32. And then we need another expression, and that's going to be primitive op of add a plus. And that's going to contain a let, which takes x2, int 10, and so it's binding 10 to x2, and then it's returning var of x2. Okay, so that's the end of the let, and we want to do var of x1. Okay, so what do we think that this should evaluate to? We have x1 is set to 32, x2 is bound to 10, and then we return 10, and then we add that to x1, so we should get interpret should equal 42, right? A little joke they threw in there for us. We're missing some parens here, I think. So let's break this out a little bit so we can read it. So this is a plus of that expression, and var So there's the end of that one, there's the end of that one, there's the end of that one, and we need an end of the program. Okay. And it reformatted it for us. So let's run the test, and this is a good place to stop. Okay, it passed. Let's see, we're not using negate, we're not using read. Okay. Easy enough to fix. Cool. Okay. So I don't know that we really achieved the achieved what they wanted in terms of the way to do dispatch over those languages where we're able to really reuse. But this is so, these languages are so simple in this case, I feel less bad about copying them. So that's where we are. If we were in Rust, we could do something like create a trait and implement that trait for those types and dispatch to the inner one if we're wrapping. We could do something similar in Gleam. We just won't have traits to drive it. So we'll see how far this goes, but we can't do the overriding thing like they do in the book here. But what we do want to go to next is defining the x86 int assembly language, and then we can turn these programs into the x86 assembly. So I think that we're going to do that on the next stream, and we'll pick up where we were in chapter 2 then. So thank you for coming. I hope you guys like this content. We're learning some Gleam. We're doing compilers, which is one of my favorite topics, and we'll find our way through this. So thank you for joining me, and I'll see you again next week, hopefully.